Hi, everyone. I'm Stanley Seibert. I work at Anaconda. I manage the open source team there, and I'm excited today to talk to you a little bit about continuous integration for scientific Python projects. So to begin with, let's say that you have written unit tests for your project. You've eaten your developer vegetables and done what everyone told you to do and gone and written some unit tests, and maybe you even have a test runner like PyTest that can, with one command, run all the tests in your test suite. That's great. That's already sort of the first step to making better software, but it is just the first step in test automation to have a test suite. Now, if you don't have a test suite, you should go make a test suite. The whole rest of this talk will make a lot more sense if you have a test suite. It doesn't have to be comprehensive. It doesn't have to have full coverage. It can literally just be one test that could run a function. There are lots of good tutorials about how to use PyTest and unit test. And since this is YouTube, go ahead and pause this video. Go make a single unit test for your test suite and come back, and I'll be here. Okay, so I will assume that you have a test suite of some sort. Now, the reason we have to go beyond just having a test suite is because one of the lies we tell ourselves as developers is that once we have a test suite, we'll always remember to run it before we commit our code. But we'll make a quick change and we'll be like, oh yeah, I'll totally remember to run the whole test suite before I push. And inevitably we forget. And even knowing everything I've written in this talk, I have made this mistake many, many, many times. So it's important to acknowledge to ourselves that without automation, we will not consistently run the tests that we have written. And that is an important thing to acknowledge, because if we don't do that, it's very easy for master to accidentally get broken and to not realize that there were functions that had been broken and you didn't know about. So we need to automate a thing so that we don't forget a thing. So what is continuous integration? Now, I didn't even remember what continuous integration originally meant until I looked it up. And originally, continuous integration was proposed as the practice of having developers continually integrate updates into the main development branch as they developed. This has basically turned into sort of how we do software development now with things like Git and GitHub and PRs and all of these other things where we're constantly making updates, many developers, and reintegrating them, as they're ready. So that's not a particularly useful definition of it for how it's used now. Now, continuous integration is often thought of as the set of processes and tools that allow you to have a development model where you have many frequent merges from many people into the main development branch. You need this level of automation because if you have all of these people doing things, it's very easy for them to step on each other. So we need computers to help us, help keep us honest and to help let us know when we're about to break something before we even realize it. So continuous integration often talks about things like infrastructure to automatically build packages and run unit tests, automated execution of other code quality tests. Maybe you run Flake 8 or something like that, or coverage to verify that your tests are actually hitting all the lines of code you have. And you can often put other tasks into your continuous integration pipelines, things like pushing documentation, uploading build artifacts. And you can make it set up so that just the act of pushing a tag to a repository kicks off your entire release process. That level of automation is possible with things like continuous integration tools. So why do you need a continuous integration tool? And I want to emphasize here that the biggest takeaway, I think, is to recognize that CI is an investment of time and effort, but it also is a reward that pays itself back if you make that effort. Good CI infrastructure will allow you to develop faster because you have less risk of breaking things if you're moving quickly. It also eliminates a whole class of bugs, which I would describe as works on my system kind of bugs, where people, forget to add a dependency or forget to check in a file. And if you are only running the tests on your own local development machine, it's very easy for those sorts of local state to creep in and accidentally make it look like things are working when they're in fact not. Another thing is we don't all develop on all operating systems all the time. And so if your main development driver is a Linux computer or a Mac computer or a Windows computer, you may not be aware of issues that will affect other people with other different platforms. And the advantage of CI is rather than having to go manually check all of them yourself, you can have every time you make a commit, it'll check on all the platforms and then tell you whether or not you've broken one of them. And this is really important to also help users who might not have the same platform as you. The other thing is this will let you turn around software releases more quickly. The last thing you ever want to do is to push all your testing to just before release time. When you do that, you will inevitably end up with fire drills and things where you're trying to find out that this thing that you broke 4 weeks ago and didn't realize is holding up your release. So CI makes you, in some sense, ready to release at any moment. And an underappreciated thing is that continuous integration systems actually make it easier to onboard new contributors by giving them fast feedback. If they are following your guidelines and writing a test for their feature, they will immediately be told by the CI system whether or not it works on all the platforms, whether or not their change has accidentally broken other parts of the system. And they get all this feedback without direct maintainer intervention so that they can, if they're in a different time zone than you, they can get feedback on their code before you even are awake to look at it. So let's talk about designing a CI workflow. Now, the first thing to remember about CI in general is that CI, like security, is a process, not a program. You do not do continuous integration just by saying, okay, I downloaded a CI program and I turned it on and now I'm done. You really need to think about it as a process and as a constantly evolving process. So first, like all processes, you have to start with some requirements. And with CI systems, you really need to think about a list of things. One of them is what code needs testing. Are you testing the master branch? Are you testing pull requests? Do you have long-lived feature development branches that need testing? Just taking an inventory and understanding what even needs testing is like the first thing that you have to do. Second thing you have to think about is how often do you really need to test? Do you want to test every commit? Do you want to test every night? Do you want to test every week? You might do different tests with different cadences. This is about being realistic about how many contributors do you have? How fast is the code being updated? How many resources do you have to run tests? There are always trade-offs here. Another question is, how many tests do you want to run? Do you want to run every test every time? Are there subsets of tests? Maybe there's a set of tests that run faster than others and you want to run those. Another one is what environments need to be tested. And this gets back to that, those other operating systems. You might need to worry about things like Windows and you don't have a Windows machine, or a Mac and you don't have a Mac. Another thing is that it's not all x86 chips now. Intel and AMD have been the dominant CPUs for a long time, but we're starting to see more and more usage of things like ARM, not just the Raspberry Pi, but even in cloud vendors, PowerPC, all of these things are starting to crop up. And if you have compiled dependencies in your code, you depend on what kind of chip the user is running. And so you may need to check those in addition to things like Python. And then what reporting do you need? A CI system that doesn't tell you anything doesn't exist. So what do you need to know? Obviously, you need to know things like what test failed. Maybe I want to have access to full backtraces. In fact, you definitely want to have access to full backtraces. Do I want line coverage of my tests? Are there other quality metrics I want to be reported back? What is the feedback loop that you really need for your testing? Do you need it to report to you over Slack or over email or on GitHub? These are all things you should think through. Now, once you've thought through all of that and made your laundry list of requirements, you should recognize that you are going to now have to make some pragmatic compromises, because what you want is probably not achievable. Running every test for every environment on every commit is just not going to work and has actually some negative trade-offs in itself. So you should really think about what's actually useful for your project with the number of developers and how fast features are being developed. And be prepared to mix several combinations of the previous slide. You might need to do sort of 3 independent sort of testing cycles. You might be testing master with the full test suite while doing a small subset of tests for pull requests, but then as part of the code review, kicking off a full run of all the tests for a pull request before you merge. Something like this that lets you make compromises that fit within your resources is going to be important to do. Second thing is to think about, where does the CI system plug into your whole development process? Don't think of CI as a separate thing. Think of CI as part of how you develop code. So here I have sketched out a pretty crazy diagram, but this is kind of how most people do development on GitHub these days. If you're going to contribute, you go fork the main repository to your developer account and you make a feature branch. You commit some code and you commit some tests that verify that code works, and then you open a pull request against the main repository. At this point, 2 things start happening. One is maintainers will start doing manual code review. They will read your code, provide feedback, that sort of thing. At the same time, in parallel, you might, for example, want your automated CI system to start running all the test suite on all the platforms you want to support. And that is also providing feedback to the developer. And then when all the feedback has been addressed, you merge the PR to master. And then at that point, you might want to run all the tests on master just to be absolutely certain master is always working. And if master works, you might then have an additional step in your CI system that will build and upload some development packages to some channel that developers can get the latest nightly builds to be able to test things out. And one of the things to note here is that this feedback loop between running the test suite on all the platforms and the developer is fully automated, which means that, again, to my point earlier about how this helps new developers onboard, this computer person loop can run at any time of day for anyone. And so this is a really great way to help new contributors get confidence that their code is working without having to constantly go around the other loop with you for manual code review. So by the time you do manual code review, you're already in a better state than if you had just gotten a PR with no testing at all. So another thing to think about is what configurations do you actually want to test? It's often described as your configuration matrix, although it may be multidimensional. So maybe it's a configuration ND array. It's tempting, and I've seen multiple projects try and do this. Usually not open source Python projects, but maybe more scientific projects, to try and restrict themselves to say, okay, testing is a pain. Let's just declare one blessed platform. Let's say it's like, Linux on x86 64-bit, and we'll just arbitrarily pick Python 3.8, something like that. And if by controlling all those variables, I will limit my testing requirements, everything will be great, and I won't ever have to worry about broken code ever again. And that's not, that is a trade-off, and there may be some projects with limited resources who have to make that trade-off. But I want to argue that investing effort in testing multiple platforms will make your project more accessible, and it will make it more accessible to users who don't exactly match your environment. An extremely, common frustration for people, this is one thing that, we run into a lot at Anaconda, is a lot of our users are on Windows. And the projects that only test on Linux and have random Windows bugs that could have been trivially fixed are a real obstacle for them. This has gotten better in recent years, I should say, with the rise of CI systems that have Windows support. But long ago, you can remember the sort of shrug works on Linux kind of mentality from developers, which really was a barrier to entry for a lot of people who maybe can't switch their platform. Maybe this is on their work machine and they can't just install Linux because that would be a good idea. So really, it's worth the effort to try and invest to broaden your user base. And another thing, and this happens more in compiled languages, I can't tell you the number of C++ functions or C++ code bases that I've run into that have had effectively, memory bugs that worked on accident. And those bugs were found by running on other platforms. So things worked just fine on Linux. And then when I ran the test suite on the Mac, it failed. And even though I didn't actually have to run this code on the Mac necessarily, by testing it in many places, there was enough sort of randomization to be able to find these works on accident bugs. Now, one thing to think about is that although you may want to test several Pythons on several platforms, you don't have to necessarily test all combinations. You'll have to use your judgment about how sensitive your project is to correlations between things. That if you check on Python 3.6 and on Windows, do you need to check on Python 3.6 and Windows at the same time? Maybe you don't. Maybe you do. So it's worth thinking about that, thinking that through, and maybe starting with a more sort of orthogonal matrix like on the left, and then moving toward something on the right if you start seeing bugs that crop up that are correlated between dimensions. So just some numbers here. I quickly grabbed these from the Conda package stats data that's public. There's a URL down there. This is package counts, not unique users. So, by and large, most of the packages downloaded are on Linux. A quarter of the users are not on Linux, though. And I would say that if you were to try and uniquify these people somehow, a lot of automated systems and servers use Linux, but a lot of hands-on keyboard shows up on Windows and Mac. And so they are, while smaller, they're still sort of important. Another thing to note is on Python versions, this is as of April, 40% is still on Python 3.6 and almost the same amount on 3.7, and then 3.8 and 2.7 are about tied. So, keep in mind, there are many Python versions. You can't necessarily just drop them as soon as they come out. And in fact, if you as a project in the SciPy space, want just sort of a default deprecation policy of what matrix should you be testing, a good place to start is NEP 29, which is NumPy's deprecation policy that was discussed quite heavily and basically advocates supporting minor Python versions for the preceding 42 months that have come out in the preceding 42 months, and minor versions of NumPy in the preceding 24 months. If your configuration matrix grows without bound forever, it will eventually eat up all of your testing resources and you'll stop making progress as a developer. So it is useful to deprecate things, and NumPy is going to follow this schedule. So it may make sense for your project to do so as well if you don't have any additional constraints either way. Another thing you're going to want to think about in your process is how are you going to do reproducible testing environments? You want to be able to run the environment with your tests both inside and outside the CI server. If you're using a CI service or you're setting up an application, you're going to want to also set up the exact same environment on your development machine for when tests break. There is nothing more frustrating than tests that break in CI and you can't make break on your machine because you can't reproduce the environment. Docker is the sort of gold standard here. It's well supported on many versions of Linux, many architectures. You can run Docker on Raspberry Pis and all of the other things. Windows support also exists for running native Windows binaries in Docker. This is something I have personally not experimented with, but it has been on my to-do list for a long time because this sounds like a very intriguing way to make reproducible environments on Windows. Keep in mind that Docker on Mac runs Docker inside of a Linux VM VirtualBox or something like that. It is not running native Mac binaries. So there is no native Docker solution for running Mac binaries on a Mac. There are some very crazy experimental options, which appear to be running sort of a Hackintosh setup inside of a Docker container, presumably a Linux Docker container. Google them if you're interested, but they are at best, probably a little bit unstable, and at worst might violate the macOS license agreement. I'm not really sure. Another thing to do is you want to script building a new test environment from scratch with or without Docker. Just write some shell scripts that will build the environment up and then call them from your Docker files. And also this lets you use them on your development machines. One note here is whether or not you're using Conda. It's good to know that Conda can install specific Python versions. So I have seen people who aren't using Conda for anything other than set up an environment with a specific Python and then pip install everything else. That is a totally viable way to set up your environment. And then one other final thing is resist the temptation to reuse a single environment between builds. You don't want to build of this commit to use an environment and then come back and use that same environment, although it is already set up and it will speed up your tests and it sounds like a good idea. You will find inevitably that state leakage from one build to the next will drive you crazy. You will really, really want to just delete the environment and build it again between every single commit. So this is a reason why scripting the building of the test environment so it is as simple as possible is important because you're going to do it a lot. And then finally, you want to think about what should be tested. There are different kinds of tests. Some of your unit tests, the pure unit tests are supposed to be very fast and test small units of code. In practice, actual practical test suites tend to be a blend of what I would consider traditional unit tests and things that are more like integration or acceptance tests that maybe test larger chunks of code or maybe the whole application. They all kind of get mixed into the test suite. But you can often in your test framework tag different kinds of tests. Which will let you slice them out. When you're running them in the CI system, you can tell your test runner to run only these kind of tests or run these other kind of tests. And you want to think about how often you want to run all these different kinds of tests because there's this trade-off of if you run too many of the tests too often, the CI is less responsive. If you have to wait an hour for your test suite to get back to you and tell you that you broke the code, that's just going to slow your development cycle. However, if you run too few of the tests, if you subset your test down so your test suite takes 5 minutes, that's great. But it will slow down development by letting bugs through that will be much more expensive to fix later when you've maybe already committed them to master or you're further down in the review process and you could have caught them much earlier. So unfortunately, no matter what you pick here, there's a risk of slowing down your development due to one thing or another. So you have to kind of fine tune it over time and see, okay, when have I failed to catch a bug? Maybe I need to run a few more tests or vice versa. So let's talk about CI services and tools. So this is not going to be an exhaustive review of all of these tools because they are changing so fast. And this talk would be out of date already. I mean, the last time I investigated all of these was pretty extensively last fall, winter when we rebuilt the NumPy test suite. So my understanding of this is already 4 or 5 months out of date. So do the research, but I'll give you some categories that you can look at. Option one for doing CI is to use a free CI service. And I would say, unless you have a specific reason you can't do this, this is the best way to do your CI. It is super simple. It doesn't require anything of you. All it requires is that you have a public repository on GitHub. Usually some of these services also have Bitbucket and GitLab support. The configuration file is centralized in a YAML file or maybe a set of YAML files, so that you just check into the repository of code you are testing. So it's very excellent in the, it's very declarative. So you're not having to find configs splattered all over the place or hidden inside of databases or anything like that. It's all very visible. And you can manage your CI configuration the same way you manage features on your application with PRs and that sort of thing. Options to look at. Travis CI is sort of the classic one. I think they were the one that made this the most popular for open source projects. They do support Linux, x86, Mac OS, Windows support is experimental, and there's even experimental ARM support, which is really interesting. This has been changing quite quickly. Travis CI is all of these services are in fierce competition with each other, and so they're always adding new features. And some of those features roll out to the free tier, which is really interesting. Circle CI is another one. They have both Linux and Windows support. Mac OS support is not free. That's on the paid tier. And then Microsoft Azure Pipelines burst onto the scene, I guess a little over a year ago, maybe a couple years ago. And they have Linux, Mac, and Windows support all out of the box. Since it's Microsoft, obviously the Windows support is very good. So I would have a look at any of these. And their relative speeds and things change constantly. I mean, at one point when Azure hit the scene, they had very generous both CPU speeds and number of parallel jobs to try and sort of get some mind share. So those things may have changed for the other services, though. A CI service basically is just a integration that you turn on. They basically supply an integration that you add into your GitHub repository so that they are notified when you have a PR, let's say, that is mergeable, so it can be merged to master. Then Travis CI will take that PR, run it through whatever test configuration you've defined in the YAML file in that repository, and then go back to GitHub and post in GitHub's at the bottom of the PR what test passed or failed. And then you can, as part of your review process, look at that and then only merge things when they've passed all the tests. It's pretty straightforward. Here's a snippet of a configuration file. This is Pandas config file. It's much longer than the screen, but I wanted to give you a flavor of it. It's a big YAML file. It's got some sections that describe how Travis CI thinks about the build staging process, that you have an install stage and then you run some stuff and that sort of thing. And so you often are putting in just run the shell script, run the shell script, run the shell script. And this is a reasonable way to set up your configuration, to put a lot of the actual heavy lifting into shell scripts and just call them from the YAML file. And the results reporting looks about like this. You see at the bottom of the PR a list of, these are various checks. There are all kinds of services out there. You can add checks, for coverage and other things. Here's Azure Pipelines reporting back that, 2 of the configurations are failing and the rest are passing. So there are some pros and cons to these CI services. The big pro is that they're free for public repositories. They have no infrastructure to maintain, and you don't have to worry about securing anything. And we'll talk about security in a bit here. The declarative configuration is just pure YAML. It's quite convenient and easy to read. And your config is version controlled, which is really important in a CI system to be able to version control the configuration of the CI system. And then often some of these services will integrate directly with the GitHub accounts and permissions so that people who have permissions on your repository can also have permissions to kick off builds on the CI. There are some disadvantages, however, in that there are a limited number of parallel jobs. Often because it's a free tier, they'll maybe give you somewhere between 2 and 10. And they'll also limit the job length, often to about an hour. And they make assumptions about the job structure. They assume sort of a linear sequence of things. Some of the services have more branching capability in the pipeline possible. But a big one is that it can be very difficult to debug problems because you don't control the infrastructure. On one hand, you don't have to pay for the infrastructure. On the other hand, if something goes wrong, it's very hard to figure it out because you can't just SSH in the machine in many cases. It's also difficult to test on special hardware. Things like GPUs and non-x86 CPUs often don't exist in the free tier. Sometimes they don't exist at all. And often the requirement to host the project publicly may be a non-starter for you. Again, for open source Python projects, this is no problem. But for certain other kinds of projects, either you can't make the code public, maybe it depends on data you can't make public to run the tests. There are all sorts of scenarios here. And in those cases, these services won't work, at least the free one, the free tier. And one thing to be prepared for is what I describe as commit-driven debugging, where you can watch me slowly get more and more frustrated here over this commit log as I am trying to figure out some weird problem with Azure pipelines that I have no way to debug outside of the service itself. And so I end up making a lot of commits just to try something and see if it breaks, and then try something else and see if it breaks. So squash merge is your friend for these sorts of PRs for sure. Our variant of option 1 is to take the free service and upgrade to a paid account. This may lift some of the disadvantages that you were having. Maybe you need it. You have private repos, but you can still host them on a public service like GitHub, but they're still private. Maybe, in some cases like Circle CI, paying lets you pick the hardware configuration that the build runs on, which can also include GPUs. So if you have a GPU code base and can pay for Circle CI, you can do your CI on the GPU and still have all the GitHub integration that you want. Other services like Azure Pipelines actually let you run your own build workers. You basically download a client, run it on the build worker. It links up with your project in their cloud, and then builds will go to your build worker, which at that point you can put any hardware in there you like, any software in, any data you want. And then often the paying will let you do more parallel jobs and longer jobs and that sort of thing. All of these systems use the same configuration as the free service, so be sure to try the free tier before you buy if you can. Just to find out if they're going to work. And I'll mention later the security issues with running workers on your own hardware, which comes up in this case. Option 2 is to run your own CI tool. Say, okay, I need total control. I'm going to download something, Jenkins, whatever. We'll talk about some options here. And I'm going to run it on my hardware, and it's going to do everything for me. And so CI tools differ in exactly how they work, but the same basic structure is that all CI tools typically have a web UI that lets you see the results of tests and maybe sometimes kick off tests. Some of them have a command line interface as well. That talks to a scheduler whose job it is to farm out jobs to different workers to build, collect the results, and put them in some result storage that the web UI can see. And oftentimes the scheduler is kicked off by an external event. So the code will have some kind of thing that can issue triggers. This may be something that pulls the repository periodically to see if there are new commits. There may be other triggers like, a time trigger, like run at 2 p.m. or something like that. And this is pretty much every CI tool has this same basic format to it. And everything to the lower left of that dashed line is something you're going to have to run on your infrastructre, some computer somewhere. It may be a cloud machine or a machine in your lab or that sort of thing. Now, there are tons of options here for apps. The old standard is Jenkins, which is very sort of Java developer centric, but honestly works with everything and has a million plugins. It's kind of the WordPress of CI systems, and that has been around a long time. Some parts of it seem a little bit old school compared to how we would do things now, but there is a plugin for everything. Actually, there's 5 plugins for everything. So it's pretty flexible, if sometimes a little bit quirky. Concourse is another one. This is very, I would say, sort of very Linux centric, but a much more modern take on things. It's really, I think, also optimized for like continuous deployment, where your goal is to like build Docker images that you're pushing into production, but you can use it for other things. GitLab is a version control system that also contains CI and CD. So it's all in one. So if you are, for example, already going to run GitLab internally for your source code, this already has a built-in CI system. And so it's worth investigating. And then the sort of a old school Python build system that's been around for a very long time is BuildBot. BuildBot is pure Python. It's very interesting because its configuration is Python. In some sense, what they give you is a big pile of Python classes and tools to assemble your own CI system out of. So it is very flexible, but can be a little bit daunting in terms of a learning curve. And there's also DIY options. I mean, for example, NumPy now has its own CI system we cobbled together. I'll talk about later from other parts. That isn't any of these things. So don't feel like you have to use one of these things, although you probably, if option 1 isn't good enough for you, option 2, you should really think about not building your own CI system unless you have a really good reason to do it. So pros and cons here. CI tools are highly customizable. You can run any hardware you want, no time limits. You basically can do anything that you can pay for the hardware of. So it's no rules, no limits for you. And it lets you keep things private that might need to be private. If you need to run tests on databases or large data sets that you can't just push out somewhere that can be seen, a CI tool running inside of your firewall is a great option. However, they're much harder to set up. There's a much higher learning curve. There are often too many options for everything. There's a sort of decision paralysis that comes with these tools because there are so many ways to do something and often so many plugins that it can drive you a little bit, it can be a little bit discouraging to get started. And depending on how the system is configured, you often will have the CI system configuration split up in a couple of places. You're running on a server, so how you set up that server is technically part of the configuration of your CI system. So unless you do some DevOps work to basically script setting up the server, where you script setting up Jenkins, where you then, so on and so forth, before we even get to the pipeline for your project, it can be hard to recreate your CI system without having logged all of that. And then, of course, there's the issue of running your own servers. There's cost, uptime, security, maintenance. All of these things now become your problem, whereas with the service, they weren't your problem. And this is where I want to insert a security warning for people that I often bring up when people talk about CI systems in their own infrastructure that people sometimes don't think about, is if you are taking a public repository and hooking it up to a CI system that runs on private machines that are inside of your institution's network, whatever that is, if you are automatically triggering builds on pull requests, you have a remote execution hole. Now, that might be an acceptable one. And the thing is with a public CI system, this isn't your problem. You don't really have to worry about what are the implications of running untrusted code on a machine because it's not your machine. Travis CI and all these places do their own mitigations and network blocking and other things. And all those machines aren't inside your firewall where you might have sensitive machines. So this is another reason why a CI service is much preferable to running your own. But if you do have to run your own, consider a couple of mitigations. One is a lot of places will require a maintainer to trigger CI manually after code review. This lets you scan to make sure that someone hasn't just stuck an Ethereum miner into a pull request to steal time from your machines. This hurts some of that feedback to new users, because if they are making commits and seeing if they work, if you have to approve everyone manually, then it's going to just slow down the feedback loop. But this may be unavoidable. Another thing you actually think about is probably firewalling these build machines, or maybe using cloud machines not in your network as these workers, where you still control the hardware, but it's completely on a separate network. And so the consequences of it running arbitrary code are less than if they were running like in a machine in your lab. So let's finally talk about some tips and tricks before we wrap up here. So big one, and this is a sort of meta tip, is that CI is a journey. It's great to write down a list of requirements. Guaranteed your list of requirements will be too much to achieve in one go. Don't try and do them all at once. Think about what is the biggest impact with the least effort and start picking them off one by one. Whenever, and this is inevitable, when a CI system does let a problem slip through, it's really valuable to stop and do a postmortem and just say, how did this happen? What allowed this to slip through? Was it because we didn't have enough test coverage? Was it because we skipped running a test in a certain scenario we didn't know? Is it because the CI was misconfigured and wasn't actually checking something that we thought it was checking? And I would say a lot of CI systems are really based on failure-driven development. Every time you fail, you fix it and you move on. And so don't let those opportunities where failures happen pass you by and not make the changes that you could have made if you stopped and looked at why this happened. It's easy to skip things like this when you're in sort of the firefighting mode of you're trying to get a release out. But if worst case, log it in an issue and then come back to it after the release. And then also you need to realize that you will have to re-implement your entire CI system periodically. On NumPy, I think we've gone through 4 entirely different CI configurations in 7 years. And that's about the cadences. Every couple of years, you will have accumulated enough tech debt and enough new requirements that you just have to start over. And that's fine. You have to accept that. To make that easier, it's good to put as much logic as you can into shell scripts, Docker files, et cetera, that are not tied to a specific CI system. You'll be able to use Docker and shell scripts with any CI system that you eventually move to. So by putting as much there as possible, you're kind of future-proofing your system a little bit. Also, by doing this, you make it possible to run old and new CI systems with the same shell scripts, and you can run them in tandem to check against each other. You can migrate to a new CI system by continuing to run the old one until you have confidence that the new one is doing what you want, and then shut off the old one. That really makes it a lot easier to do upgrades without having to kind of stop the world and hope that the new thing is going to work. And then another thing to keep in mind with this is that some contributors actually like doing this stuff. I know a lot of developers look at this as kind of a tedious thing that takes their time away from doing code review and feature development and that sort of thing. But some people like to do this. So it's really good for your project to find and mentor maintainers who want to focus on CI tooling and test infrastructure. This is an important contribution that requires a different set of skills than maybe contributing to the code base in terms of features, but will also help your project run a lot smoother. The yak is in the eye of the beholder, I guess. So look for help here. Another tip is, and this is not really an issue unless you are rolling your own test infrastructure, but a subtlety people don't realize is that when you are testing PRs, you don't want to test the commit on the PR branch, you want to test the commit with master merged into it, because that is ultimately what will happen when the PR is merged. You can have PRs that pass tests on the branch, like that commit 1A might pass just fine, but it actually creates a problem when merged into master because of commits 2 and 3 later that occurred ahead of it. So you can do a local merge when you're scripting out doing the test, and often a lot of CI systems like Travesty and others will automatically do this sort of thing for you, so you often don't realize it's happening. But this is what you are actually testing, is that merge and not the most recent commit of the PR itself. Another tip is determinism. You want to make your system as deterministic as possible, because the number one cause of frustration is not being able to recreate a failing test when it happens. So you want to be able to define your test environment with config files and then verify that configuration. You want to call conda list or pip list in the build, capture that output, just to check exactly if what is there is what you think is there, because this is probably the number one cause of weird bugs, is you don't realize your CI system is using a different package version than you think it is. You want to make sure just as good test hygiene. You want to make sure tests don't depend on order of execution. So you really want to make good use of fixtures to set up and tear down state between tests. This is another way if tests run in a different order in your CI system than on your local machine. You may not realize that order is causing test behavior to change. And then one that is also, I think, particular for numerical applications that I have seen and made many times is, do not confuse the need for arbitrary test data with random test data. Oftentimes you're like, I need to make an array with some arbitrary data, pump it through this function, and make sure that the answer I get back meets some basic requirements. There's a temptation to just call the random number generator to generate that array of 50 arbitrary values, which is fine. But if you do that without seeding the random number generator, you will get a different array every time, as you would hope for a random number generator. But that will mean that you may have tests that fail in your CI system that pass on your development machine, or that fail 10% of the time in the CI system and pass on your development machine. That is just going to make you nuts. So you really, really want to make sure that when in your test environment, whenever you are using a random number generator for anything, you have seeded it with some fixed seed. You may want to separately do some fuzzing and generate large amounts of random data and then capture the ones that cause tests to fail and make new test cases. But you don't want your CI system just doing that for you accidentally. That will cause a lot of confusion. Another strategy is, whenever you are testing, you want to fail as fast as possible. You want that feedback loop to go as quickly as possible. So often tests run in some fixed order. On the left here, I have, let's say this is some pull request I've made, and tests 2, 5, and 8 have been changed. Those are in source files that I have touched for some reason, or maybe I've added test to or something like that. Rather than run these in this order every time, if you can organize your CI system to maybe run the tests in files that have been changed in this PR first, and then bail out if those fail. Those are the ones most likely to fail. Oftentimes features are self-contained, and so you want to first check, does the feature actually work with the new tests or the modified tests that you've made? And if it doesn't, there's no point in running the whole rest of your test suite. You should go fix that problem first. Speeding this loop up is huge, and this is a big improvement we've made in the NumPy test suite, is to use Git to find all the test files that have been modified and run all of them first, and then run all the tests. Another thing that we've done more recently is downstream testing. So when you are running your CI system, you are implicitly checking if maybe new releases of my dependencies, whatever versions you're grabbing. Oftentimes a test suite will just say, give me the latest Dask, matplotlib, etc. Do those break my code? I have some unreleased code and I'm checking it against released packages. I'm effectively checking if the upstream packages have, maybe if they've changed, have they broken my code? There's another direction you can think about doing this, which is, if you are a library that is used by other projects, you might want to know if you are making a change that is going to break them downstream. This is especially important in projects where the definition of what is a public API is maybe not super clear for historical reasons. And, also it's Python. So if people want to go call a function, they can call a function. There's no such thing as a private function, really. So it's useful to have some sort of signpost projects that are heavy users of your library that you can vet whether or not, if you were to do a release today, would you break them? And so this is something we're calling downstream testing. I'm not actually sure what the official term is for this, but you're basically running the test suite, in this case for app 1 and app 2, against in an environment where you have an unreleased version of your library and see if they still pass. We did this enough that actually one of our developers, Val, put together a package called Texas BBQ because it smokes out bugs. Anyway, so that it's a really handy project for basically scripting, running other people's test suites with some unreleased version of your project. So I would definitely take a look at that. It's been very helpful for us, especially as we've done a lot of heavy refactoring with NumPy lately. And then last thing I want to mention, or maybe not the last thing, is don't be afraid to remix and mix tools. You don't need just one CI solution to meet all your requirements. You might need several overlapping solutions, and that's okay. On NumPy, for example, we use Azure pipelines to run a slice of tests, basically. We actually stripe the tests across many workers on every PR commit so that our contributors get fast feedback. That's really important there. However, that can't test all configurations comprehensively. So we also have a system based on actually a combination of Airflow and Dask, which I'm not going to talk about in this talk, that does full testing on every platform combination, does all of our package build, that sort of thing. That has to be manually triggered by developers for those security reasons I mentioned. And then we're also using Circle CI because they have extra queue slots that, it doesn't eat up our Azure pipeline queue slots to do all that downstream testing with Texas BBQ. And so we actually have 3 entirely separate CI systems that we're all running at once. And this is something that you may need. Don't try and do it all with one tool if it's not actually going to solve your problem. Another thing is to make sure that this is a mistake that we've made a couple times, is make sure that you're testing build artifacts, not just source. So oftentimes when people script their build process or their test process, they'll do the top line here. They'll have their thing download the source, build and run the test locally, maybe in some local build environment. If those pass, maybe as a separate step or even a separate job, they'll then build the packages and upload packages. And this sequence seems logical. Why would you want to build and upload packages if the tests fail? But there's actually a hole here where there's something you're not testing, and that is, do your packages as built work? Your code might work in some source checkout, but that doesn't mean the packages do. So a better way to do this is to download and build the packages. Don't even run the test suite. Then create a new environment separate from the build environment with that built package. Run the tests in that new environment with that package. That now verifies that both the code and your packaging of the code are correct. And then if that works, upload the package. This bottom line is actually how conda build works. And it's again, a subtle thing that is when you break up these steps and maybe split between jobs, you might overlook the sequencing. But this is it's easy to, for example, have code that passes tests, but you've actually missed something in your manifest, and so your wheels don't work. Made that mistake many times. You want your CI system to catch that for you. So to summarize, a good CI system will improve developer productivity and make it easier for new people to get involved. But don't get too caught up with all the tool and service options. Start by thinking about your requirements. What do you need to run? What platforms do you need? What feedback do you need? And I would say, again, CI services are a great way to get started quickly. If you can use them, it's the best choice with the least overhead for you. But CI applications will give you more control. So if you need it, that's where you'll be. And then always, as I mentioned before, CI is a journey. Don't try and do it all at once. Invest the time in incremental improvement and use as many or as few tools as you need. Don't feel like you need to find the perfect tool. If you have to use 2 tools, do it. And recruit contributors who like this stuff. I personally actually like working on CI and automation, and there may be other people out there too. And getting those people involved in your project takes that off the plate of people who maybe don't like to do it and want to work on something else. So this is a way to help sort of spread around the load and improve the quality of your code all at the same time.